Hello, this is Tish Nichols, and this video is on conservation of charge and charging. It is one of the most important videos for the rest of the year to understand, and also pretty conceptually challenging. So brace yourselves and get ready to really focus. So we're going to start by defining a new variable. We've talked about charge a little bit, but since it is a thing in the world that can be measured numerically and can change, we can actually make it into a variable. Now, unfortunately, the symbol that scientists use for charge is a little bit weird. It's a Q, it's a lowercase q, so when you see Q, you know that we're actually talking about charge. The units for charge will be the coulomb, which is a capital C, which means that we measure charge in number of coulombs. And for the purposes of this unit, we are basically going to make an assumption that all protons have a charge of positive 1 coulomb and all electrons have a charge of negative 1 coulomb. Neutrons, of course, are neutral, won't really factor into anything, but just so you know that they have a charge of 0 coulombs as well. Those little asterisks basically mean I'm lying to you a little bit here. The charge of a proton and electron is not exactly 1 coulomb, but they are equal to each other and opposite to each other. So we're just trying to keep the math simple. So we are going to make an assumption there. So the most important thing about charge is that it is one of those super important and rare conserved variables in the universe, which means if you have a closed system, that the total or the sigma charge in that closed system is going to be conserved. Of course, the biggest system, the really only truly closed system, is the entire universe. And in our universe, it appears that we have exactly as many protons as electrons in the universe, which means that the sigma charge of the universe system is actually 0. For every positive one, there's a negative one, and so you add those together and you get 0. Most closed systems that are smaller than the universe will also have a charge of 0. When you look around at all the things around you, like a chair or your pencil, it has protons and it has electrons, but it has the same number of each. So pretty much everything around us has a charge of 0 unless we've done something specific to it to allow charges to move on or off, which is the topic of the rest of this video. So if you're interested in finding the total charge or the sigma charge stored up in a smaller system, it's pretty straightforward. It just means you add up the total charge of the protons, which are positive, and then the total charge of the electrons, which is negative. You can think of that as adding the negative or subtracting. It doesn't matter either way, as long as you understand what's happening there. So for example, in the system shown below, there are 4 protons, and they are in the nuclei of those atoms. And so those 4 protons would have a charge of +4. And there are 3 electrons floating sort of around the outside of those atoms, and those would have a charge of -3. So overall, the system is the sigma q, or the total charge in the system, is positive 1 coulomb, which is a relatively small positive charge. You could have a system that has 4 protons and 4 electrons. We talked about that on the last slide. In that case, the sigma q of this system is 0 coulombs, and this is typical of most objects and most systems around us. Or you could have an object that has extra electrons. So for example, this system has 4 protons and 7 electrons, making that +4 -7, or a total sigma q of -3. That's going to be a larger charge, and it happens to be negative. So before we talk about how we can get objects with a neutral 0 charge to have a positive or negative charge in the first place, I want to mention an important process known as polarization. Polarization is fundamentally the idea of taking a neutral object and making 1/2 positive and 1/2 negative, even though overall the object is still neutral. It's got the same root as poles. You've heard of the poles of the Earth, right? We have a North Pole and a South Pole. Polarization is kind of the same way, except for you end up with an object with a positive pole and a negative pole. And the way you do that is you take your happy little neutral object that has balanced protons and electrons, and you bring an outside object near to your system. You don't touch them to each other, you just bring it nearby. And that external charged object is going to exert electric force on the charges in the neutral object, and it's going to cause those charges to be pushed or pulled from one side to another. So for example, um, we've got a big negative object on the left. We're not talking about how it got negative, we're just going to say it's got a lot of extra electrons. And on the right, we have an object that's going to be neutral. Right now it is, I've only shown the protons in it, but there you go. If you put those 4 electrons in, what you'll notice is those electrons are actually moving to the right half, right? And they do that because they're being repelled from the negative object that is nearby. So this is still a negative, or this is still a neutral object. We still have 4 protons and 4 electrons, but we have a positive half on the left and a negative half on the right. One interesting effect of polarization is that neutral objects are actually attracted to charged objects. And the reason they are is because the half that is closer to the charged object has the particles that are being attracted. And so that half is pulled. The other half is being pushed away from the charged object, but the push is a little bit weaker than the pull because that half is further from the negative object than the other half. And we know that there is an inverse relationship between the electric force and the charge. So that's something that kind of pops up as an advanced problem later on. But in general, understanding that neutral objects can be polarized and divided into a positive half and a negative half is pretty important. So the rest of this slideshow is talking about charging, which are the processes by which we take our neutral charge systems and we move charges in or out so that they end up with an unbalanced sigma q. An important note is that all charging happens by the movement of electrons into and out of the systems. Remember that the electrons are the particles that exist on the outside and they're not bound in the nucleus. In physics, we never move our protons. And the reason is if you pull something in or out of a nucleus of an atom, you get a nuclear explosion. So in this class, we're going to try to avoid nuclear explosions. So we're going to remember that all charging happens by the movement of electrons, not protons. Of course, you can get a positive or negative object by moving electrons. You'll get a negative object if you add electrons, more negatives, and you'll get a positive object if you subtract those electrons, because then you are left with unbalanced protons in your system. So you can get charging positive or negative by the movement of electrons. Don't move the protons. The first kind of charging process we're going to talk about is known as friction charging. Friction charging is probably the one you're most familiar with in your life because you rub your feet on the carpet and you notice that you can zap a sibling when you touch them with your finger. So friction charging happens whenever you are rubbing 2 different insulators against each other. Rubbing 2 different insulators always transfers electrons from one to the other. Insulators have a certain property of kind of electron grabbiness. Some materials really, really like to grab electrons, and other materials are not so possessive of their electrons. So if I take 2 different materials, they might start off neutral. They both start off with the same number of protons and electrons, sigma q of 0. But as I rub them, whichever one of those 2 materials is like greedier for electrons will steal the electrons off of the surface it's touching. This is why the rubbing is so important, because when you rub 2 objects, you allow those surfaces to come into contact, you allow the atoms to come close enough to kind of steal electrons off of the other material. So you'll notice that object on the left, the green object, now has a positive sigma charge because it lost electrons, and the orange object on the right now has a negative sigma charge because it stole the electrons off of the green one. Of course, if you considered the entire system, the green and the orange object together, you would find that sigma q is still 0 for that system because charge is conserved in the universe, right? We didn't create or destroy any electrons, we just moved them around. I mentioned that some materials have a certain desire or grabbiness for electrons. This is known as the electrostatic series. It basically just is something scientists have determined experimentally. They rubbed a bunch of things together and figured out who grabbed the electrons. So in general, there is kind of a hierarchy or an order of who grabs the electrons. Rubber is the grabbiest. Rubber ends up with the most electrons, and then plastic, and then a variety of other materials. But notably, cotton and fur are types of hair, okay, from different animals, and so those are often used in friction charging. And on the far other end of the spectrum, the materials that don't care about electrons and often get their electrons stolen from them, glass and different kinds of other materials like that. So you don't need to have this table memorized. On a test, we'll always tell you which material grabs the electrons, but I just wanted you to know that it was kind of set up experimentally by scientists. The second kind of charging is known as contact charging. Unlike friction charging, contact charging only works with conductors. And the way it works is you have two conductors that have unequal sigma charge, so different amounts of total charge. And when you bring them into contact, since they're conductors and electrons can flow easily, the electrons are basically going to redistribute themselves. They're going to spread out as far as possible so that when you're done, the two conductors will actually have the same sigma charge. So for example, on the left, we have a conductor there with a sigma q of +6. So 6 more protons, 9 protons, 3 electrons, sigma charge is +6. And the one on the right has a sigma q of +2 because it only has 2 extra protons. When you bring them into contact, though, since those electrons were kind of all piled up on the right before, they're going to spread out a little bit further. And 2 of those electrons are actually going to move to the left so that we have the same number of electrons in each half of this system. So when the left one gained 2 electrons, its charge went down by 2 because we added 2 negatives. So it now has a sigma q of +4 coulombs. And the one on the right, of course, lost 2 electrons, and so now it also has a charge of +4 coulombs. Quick little note, you can see conservation of charge if you consider them together as a system, right? On the left, the entire system started with a charge of +8, and on the right, you still have a charge of +8. It's just located on different objects, but we again have not created or destroyed any electrons or protons. You may have encountered the term grounding or heard of a ground wire before. Grounding is kind of a little special case in contact charging. It's basically when you take an object in the world and you connect that object to the earth by a conductive wire. And you would do this because you basically want to use earth as the biggest either source or sink of electrons. Basically, Earth can provide infinite electrons to an object, or it can take infinite electrons. It's such a huge object it barely notices when you add a handful of electrons to a small object. So grounding, if you take a charged object and you ground it, it's going to become neutral when it connects to the Earth because Earth is so big, we basically don't even notice any minor extra electrons. However, it is also possible to use grounding to give an object a charge, as you will see in the next slide. But the word grounding just means connecting an object to the ground. The last kind of charging is known as induction charging, and it's probably the most complicated, but also probably the most important in kind of industry and engineering. So induction charging uses a combination of polarization and grounding to give a charge to a conductor that starts off neutral. So we start with this neutral conducting object. That's just a neutral metal sphere of some kind. And step number 1 is to bring a charged object near to that conductor. We talked about this earlier in the slideshow. What happens is the conductor polarizes and we end up with a positive half and a negative half, although we are still neutral. And then if you add that ground wire in that connects the conductor to the earth, what will happen is the electrons will either run away onto Earth or run from Earth onto the conductor, depending on whether they're being attracted or repelled by that negative rod that's brought in from the other side. In this case, since that rod is negative, right, it's going to push away the electrons in the neutral conductor, and so it's going to actually push them onto the Earth. If you then remove the ground wire, you will notice that the conducting object is no longer neutral because it lost some of its electrons, and it now has an overall sigma charge, which is positive, or the opposite charge from the object that you brought near it. So this is a pretty cool way of charging an object using the Earth as a source of those electrons. So this was a lot of information. You might be asking yourself, why do I have to understand this? Why do I have to understand the movement of electrons from objects to other objects? Um, well, the short answer is that electrons stored on an object stores something known as electrical energy. And when you have electrical energy, we can take that energy and transform it into, of course, all of the magical charged objects in your lives, your cell phones, your computers, your TVs, the heaters in your house, your toasters, right? So being able to harness the power of charged objects has really allowed humanity to develop technology that we wouldn't have been able to do otherwise. Might be worth mentioning at this point that electrical energy is actually a variable as well. It's going to be a big E for energy and a specific type, which is electrical, so E sub E. And the units of all energies are going to be the joule. Defining energy is actually a little bit of a tricky thing, right? You know if an object has electrical energy because it lights up or heats up or makes sound or toast. But in general, you could sort of define energy as the stored up ability to do work that makes something happen in the world. In terms of electrical energy, of course, if you see a shock zap something, or you can see, charge moving from one object to another, you know that that object had stored up electrical energy. And the more we can pile the electrons onto an object, the more charged we can make our objects into the smaller space. That is going to allow us to store maximum electrical energy, which eventually we'll be able to use to do something useful in the world. Okay, we've reached the end of the video. Take a look at that essential question, which is how do objects end up with an unbalanced sigma charge? And go ahead and jot down any questions you might have, and hopefully we can have a good discussion about this in class. Thanks.